All right, number 9 says a solution contains initial concentrations of 0.2 molar of magnesium 2 plus and 0.4 molar hydroxide. A percent precipitation of magnesium 2 plus will be. And so, so how did you guys do number 9? Just, anytime you're dealing with precipitation or solubility, you set up the KSP equation, right? So just start off with that. And then initially you're given 0.2 molar, 0.4 molar. All right? And then what would you normally do in a situation like this? Well, you need the KSPs. The KSPs I wrote a bunch on the board. KSPs and KFs. They take too much space. Unless there was room in here, I would put. If there's room in the little box, I'd put it in there. If there wasn't, there wasn't. And so, if you're given a situation like this, what would you normally do? I'm sorry? Well, QSP is going to be greater than KSP. KSP is quite small. It's like 10 to the minus 8, 10 to the minus 8, 11, 10 to the minus 11. Yeah, that's way too much in there. Yeah, that's going to be like 10 to the minus 2, which is going to be huge. This is way too much. It's going to precipitate out, right? And so, in a situation like this, automatically I would just reset. You got to be careful who you talk to because I make up so many words because like I told you, when I study or when I look at something, I try to explain it in my own words, which you shouldn't probably memorize. You should probably think of your own words to do this. But I would just reset this because it's a stoichiometric, right? And then I would just solve for S. Okay, once you solve for S, that's the amount of magnesium remaining out of your initial. And so you can calculate the percent remaining, which would be percent remains would be S over 0.2, which is your original initial, times 100%. And therefore, percent precipitation is just 100 minus the percent remaining.
Okay, why does S represent our initial? Like,
What's that?
well, what's S representing there?
S represents the solubility of magnesium hydroxide. This is not a common ion. This is just, because if it were common ion, one of these would be in excess. This is why I said yesterday the lead and the iodide have to be in a 1 to 2 mole ratio. Otherwise, it's a common ion type problem because let's say if the hydroxide were 0.8 molar, then I'm going to have excess hydroxide left over and it's a common ion. So solubility in a common ion type problem, right? Or if magnesium was in excess, then that would be it. Okay, and so this would be the way to solve that. You can approach equilibrium from any direction. That's one thing you get from chapter 15. As long as you don't lose any atoms or gain any atoms, all the atoms are there. It doesn't matter where I start. I could have started this equilibrium at 0.1 and 0.2 to reach the same exact thing, except you have to look at your original initial conditions because that's how much magnesium. So when I said there are two ways to figure out the solubility of lead 2 hydroxide, one way is just make up the concentration, 0.1 and 0.2 molar. And then that's going to be way bigger than in KSP. The QSP is going to